The objective in this video is to understand the proof for the L'Hopital's rule. L'Hopital's rule is used a lot to calculate very complicated limits. When we have a limit of a function that has 0 in the numerator and 0 on the denominator, then that limit might be a bit difficult to calculate. We're going to use L'Hopital's rule, but before that we need two theorems, and those are actually two very important theorems. The first one is called the mean value theorem, and it says that we have a function f continuous on the closed interval and differentiable on the open interval. Then there exists a number x such that this happens. And now it might seem a bit complicated what it's saying, but it's actually not at all. Let's see with this example. We have the interval AB, and let's say that this is f of a, and here is f of b. And our function is continuous and differentiable on the whole interval, so it's going to be something like this, maybe. So what this is telling us is, well, if we draw the second line through a and b, that is this part right here, this is the second line, and it's this, then there exists some number x inside the interval such that the derivative at that point, so the tangent line at that point, has slope equal to the slope of the second line. So in this case it would be a point around here, because when we do the tangent line it has the same slope as the orange line. So this is the mean value theorem, and it's very, very useful. In particular, it will be useful for us to prove L'Hopital's theorem. So let's go ahead and check out the proof. We're going to define a function, h of x. And this function might seem a bit weird, but you'll understand in a minute why we define it this way. We define it as f of x minus the second line, f in b minus f in a, divided by b minus a, and all this multiplied by x minus a. Now this h of x satisfies the following. Well, first of all, it is continuous on the interval, and it is differentiable also in the interval, because it's just a f of x which had those characteristics times some constant multiplied by x minus a. Now when we evaluate h in a, we have f in a here, and then this will give us 0, because x minus a in a is just 0. So h in a is actually f in a. Now also f h in b, when we do this we have f in b here, and then minus b minus a, with this b minus a in the denominator would cancel, and we get f in b minus and minus, it's plus f in a, so f in b and f in b would cancel, and we would get f in a. So it's the same in both extremes, and as we said, h is continuous and differentiable. So then we can use Rolle's theorem we saw in our previous video, which said that there exists some point x inside our interval such that h prime in that point is equal to 0. So 0 is going to be equal to h prime in x, and h prime in x is just differentiating this function. So we have f prime in x minus, and this is a number multiplied by x minus a, so the derivative would be just this number. So now this is equal to 0, and then f prime in x is equal to this other number. And this is what we had as the mean value theorem. And the mean value theorem is very important maybe the result itself might not seem as much, but there are a few very interesting consequences of it. So a few things we can use mean value theorem to prove is that if we have a function f such that f prime in x is equal to 0, and let's say that this happens for all x in some interval ab, then we can say that f is constant on that interval. We can also use the mean value theorem to prove that if we have two functions, g and f, such that f prime in x is equal to g prime in x, and if this happens for all x in, again, some interval ab, then there exists some constant c such that f is equal to g plus this constant. And the way we prove the second one is just using the first corollary for f prime minus g prime. And now we're gonna have a look at this other mean value theorem. It's called Cauchy's mean value theorem. It's a generalization of the previous one. Let's see why it is. We have two functions, f and g, continuous on the closed interval and differentiable on the open interval. Then there exists a number x such that this happens. And I know this might seem like extremely complicated, but what we can actually rewrite it as if g in b is different from g in a, and if also g prime in x is different to 0 for all x in the interval where the function is differentiable, then we can write this equation as f in b minus f in a divided by g in b minus g in a, and this should be equal to f prime in x divided by g prime in x. And now what I meant by it's similar to what we had before, it's a generalization, sorry, for the mean value theorem, is if g of x was equal to x, then g in b and g in a would be b and a, and g prime would be 1. So this gives us the mean value theorem. Okay, so let's go ahead and look at the proof. And the proof is extremely similar to the one we saw before. We're gonna again take a function, h of x, and this function is gonna be f of x multiplied by g in b minus g in a, and then we subtract g of x multiplied by f in b minus f in a. And you probably already know how to continue, because the same property we used before is going to apply here. H is continuous and differentiable, and also h in a is equal to f in a times all this minus g of a times all this, and well, some terms will cancel out, so I'll leave it to you to show that h in a is f in a times g in b minus g in a times f in b, and this is equal to h in b. So then again we can use Rolle's theorem and say that there exists a number x in AB such that h in x is equal to 0, h prime in x. So let's calculate h prime. So then 0 is going to be equal to h prime in x, which is equal to, well, we have that this and this are both constants, so this gives us f prime in x times the constant minus g prime in x times the constant. And there you go. This is exactly what we were trying to prove, because we had it f in b minus f in a, the constant, times g prime equal to the other constant times f prime. And this is what we have here. Okay, so now comes the most important moment in this video. We're gonna use Cauchy's mean value theorem to prove a very, very important rule called L'Hopital's rule. And we're going to use this rule to calculate limits when x tends to some number a of quotients of functions in the particular case where f and g both tend to 0 when x tends to a. So for those cases where we have 0 divided by 0 on the limit, we'll probably be using L'Hopital's rule. There are some examples where the rule doesn't work, but in most cases it does, and it's extremely easy. So what it says is we have two functions f and g such that the limit when x tends to a of f and of g is equal to 0. And we also, and this is super important, and this is very important, we suppose this limit exists, the limit with the derivatives of f and of g. So that division between f prime and g prime exists. Then, so only when this exists, then we can say that the limit with the derivatives is equal to the original limit we wanted to calculate. I don't know how to stress this enough. We first have to solve this limit, and when we can say, okay, this limit exists, then we can say, okay, then it's equal to the original one. Okay, we're gonna see this with an example, so for now let's just focus on the proof. So we're gonna start by saying, suppose that the limit when x tends to a of f prime in x divided by g prime in x exists. So because this limit exists, we can say two things. First, that there exists some positive number delta, such that f prime and g prime exist for all x in the interval a minus delta, a plus delta. Because we know that the definition of a limit implies this, the limit is a local definition. And the second thing we can say is that g prime in x is different to 0 because we are dividing by it, except maybe at a. And this except maybe is because we're taking limit. So we're not actually evaluating g, we're just taking the limit. So maybe it is 0 at a, but we can't say that. All we can say is that it's different from 0 because we're dividing by it on some neighborhood of a. So now what we're gonna do is we're gonna change the values of f and g at a. So what we're doing is the following. Let's say that this here is a, and f of a have this value. But we know that the limit, if this is the 0, we know that the limit of f, and the same for g, was 0. So we know that our function is doing something like this. Then it didn't have value 0, or maybe it did, but and then it was like this. It could be different, but what I'm saying is the limit was 0, so it was sort of approaching that point. And what we're doing for f and g is saying, hey, okay, take this value right here, make it continuous. So basically we're grabbing this point and just pushing it downwards or upwards, depending on the value of f of a and g of a. So we're making it 0. We're saying, hey, make f in a equal to 0 and the same for g. This won't change our problem at all, right? The limit will still be 0 and everything will still be great. The only thing that changes is that now f and g are continuous, because we didn't notice at first. So what we do is we take some number x in the interval a plus delta. And what we're going to do is we will use Cauchy's mean value theorem on the interval ax. And then we should do, but I'm not going to do it because it's going to be the exact same thing, the same for x on a minus delta a, and using Cauchy's mean value theorem on the interval x a. It would be the exact same thing, so I'm gonna stay with this first case. So one thing we can say is that g of x is different from 0, because if it was 0, let's say there existed an x1 equal to 0, then g prime in x1 is equal to 0, and this will contradict number 2, where number 2 is this. We said that g prime was different from 0. So now, using Cauchy's mean value theorem, we know that there exists some number alpha x. So alpha is a number that will depend on x on the interval open ax, such that f of x minus 0 multiplied by g prime in alpha x, this is just Cauchy, is equal to g of x minus 0 multiplied by f prime in alpha x. And this is equal to just saying f of x divided by g of x is equal to f prime in alpha x divided by g prime in alpha x. Now, because alpha x was in the interval ax, then alpha x tends to a when x tends to a, because we're just making the interval smaller and smaller. So then the limit when x tends to a of f divided by g is, because of what we have here, this equality is going to be the limit of f prime in alpha x divided by g prime in alpha x. And this is changing the variables because we have this. We can just call it limit when y tends to a of f prime in y divided by g prime in y. And this is just L'Hopital's rule. Now, the most important thing, as I have said before, is that we are starting the proof saying, suppose this limit exists. This is super, super important, and I cannot stress this enough. We'll see now with the problems. Let's say we want to calculate the limit when x tends to 0 of x divided by tangent of x. Well, using all our knowledge of limits, we didn't know how to calculate this, because when x tends to 0, x also tends to 0, and tangent of x tends to 0. So what we do is we call f to our numerator, that is x, and g, our denominator, tangent. Now f prime is just 1, and g prime is secant squared of x, which is equal to 1 over the cosine of x. So what we do is we evaluate the limit of f prime in x divided by g prime in x. This is the limit of 1 over secant squared of x, and this is just 1. So then here we can actually say this limit exists. And then by L'Hopital's rule we can finally say that the limit when x tends to 0 of x divided by tangent of x was actually equal to the limit of 1 over secant squared of x, and this one was equal to 1. And so we just calculated this very complicated limit using L'Hopital's rule. Let's look at another example. Now we have the limit when x tends again to 0 of cosine squared of x minus 1 divided by x squared. So when x tends to 0, cosine tends to 1, so we have 1 minus 1 is 0, and x squared also tends to 0. So as before, we just called this function f of x and this other function g of x. We calculate the derivatives, so f prime in x is just gonna be minus 2 cosine of x times sine of x, and we can rewrite this as minus sine of 2x. And g prime is 2x. So as before, we calculate the limit of f prime divided by g prime, so minus the sine of 2x divided by 2x. But again, when x tends to 0, sine of 2x also tends to 0, and when x tends to 0, 2x obviously tends to 0. So what do? Well, we can use, or we can try and use L'Hopital's rule again, and we say now this function will be my f of x and this other function will be my g of x. So now f prime in x is gonna be minus 2 cosine of 2x, and g prime is just gonna be 2. And we calculate the limit of our new f prime divided by our new g prime, so minus 2 cosine of 2x divided by 2, and this is just minus 1. So then what we can say is this limit exists. Then by L'Hopital's rule we know that the limit when x tends to 0 of this one minus sine of 2x divided by 2x is going to be the same as the other one, the limit when x tends to 0 of minus 2 cosine of 2x divided by 2, and this one was equal to minus 1. So then with this we say, hey, but this limit exists. Then again, by L'Hopital's rule, our original limit, that is the limit when x tends to 0 of cosine squared of x minus 1 divided by x squared, is equal to this other limit of minus sine of 2x divided by 2x. and this limit was equal to -1. So we were able, again, to calculate a limit we weren't able to do before. And this is all using the very strong L'Hopital's rule.